Asyle, the engineer, and the island. Week 49, Day 1. It's a new week, and I've officially been on the island for 12 months. However, because the months I've been recording have had exactly 28 days, I've still got 1 month and 1 day left to go. Come to think of it, why don't calendars have 13 months all the exact same size instead of 12 months with odd numbers of days in them? It would be so much simpler, and the one odd day at the end could just be a New Year's holiday. It probably has to do with the fact that most early calendars were based on lunar cycles. In any case, I've got 1 month to go before I think I count as an official and probably permanent resident of the island. Again, I'm not sure how to feel about that. It rained again today, lightly, so after my microbiological studies, I went looking for something else to do around the base, since I couldn't do a normal maintenance day today because of the rain again. I decided to start with the underground equipment, and while the helical ramp and elevator were still new enough that they hadn't incurred significant wear, I did notice something odd already with the geothermal turbine. Firstly, it smelled quite badly of hydrogen sulfide, but this was nothing new. It smelled from the moment it started spewing steam. But what was unusual today was that I noticed a buildup of pale sulfur crystals around the various seams where steam keeps getting out. The water in the reservoir also had a sharp taste, indicating the presence of dilute sulfuric acid, and a ring of crystals had formed around the edge from the warm water evaporating. Most of them just looked like sulfur, but a few resembled the sulfide minerals I've been mining. All of this painted a picture for me of what was going on deep in the earth, and gave me an idea as well. It's quite likely that I've hit a pocket of magma, and the circulating water is allowing sulfur and sulfide minerals to diffuse out of the magma and into the water, like the natural hydrothermal vents that form the mineral veins I've been mining. If I can pump more sulfur down there, it'll dissolve more metals out of the magma, which will in turn dissolve into the water. I can then extract those metals from the water using electrolysis, and I won't need to mine anymore. I'll basically have an unlimited supply of metals that I can draw out of the earth like water from a well. It's not going to be quite that simple, though. The increased amount of sulfuric acid I'd need to add to the water would risk turning all the wooden pipes and turbine discs into charcoal, but that's a small problem compared to the fact that I can't just stick my electrolysis plates in the reservoir, because without knowing what metal sulfides are in it, any resulting plates will be made of a metal amalgam with virtually no useful properties and which I'll never be able to separate. I need to somehow separate the metals while they're dissolved as sulfides. I think this is normally done industrially using chemicals, but I think those are mostly used to separate trace metals from an otherwise pure ore. The only reliable thing that separates one metal from another, besides its electron count, and therefore its chemical properties, is its mass. A long time ago, I had an idea for a machine to extract rare earth metals from mineral deposits more effectively than existing industrial processes by using electrolysis. I called it an electrolytic-centrifuge, or electrofuge, and the way it worked was that a conical electroplating surface, or mandrel, was made to spin, and centrifugal force would separate elements into different bands based on their densities. Heavy metals would stick to a larger radius, and lighter metals would stick to a smaller radius. There were several problems with this design, though, that led me to eventually scrap the whole thing. Starting with the fact that there was nothing to stop the lighter metals from collecting on the heavy metals radius, other than the heavy metals crowding them out, which I couldn't count on because of the law of diffusion. It's different from a purely mechanical centrifuge, which separates solid particles that are in suspension, not solution. Secondly, as the metals would build up on the mandrel, they would effectively increase its radius at those bands, causing them to start collecting the wrong material in layers, like a jawbreaker. Same thing would happen if I rotated the container instead of the mandrel. In thinking about it again, however, I realized I had to find a way to make it work, because I really needed those metals, and the natural deposits in the lava tubes are going to run out sooner rather than later. I spent a couple of hours in my office scribbling equations and bashing my brains against the problem. I thought I could maybe use a system of belts to separate one metal from the solution at a time, the lightest or heaviest, fixing the jawbreaker problem. And for a while, I thought it was pretty clever. However, the more I did the math, the more problems I found, and the more it looked like the physics just weren't having it. The equation for centrifugal force is F equals mv squared over r, where m is the mass of the object being swung around, in this case the metal ions in the solution, v is how fast they're going, and r is the radius of the circle they're being swung around in. The equation for electrical potential energy is PE equals QV, or FD equals QV, where F is the force being applied, D is the distance it's being applied over, Q is the charge of the particle, in this case the dissolved metal ions again, and V is the voltage between the electrodes. The centrifugal force needed to be less than or equal to the electric force in order for an ion of a particular mass to stick to the mandrel. So if I wanted to find, say, the voltage that would be required, the equation would be V equals dmv squared over RQ. And I quickly found that V squared term to be a big problem. Because voltage increased exponentially with particle velocity, instead of linearly like all the other terms in the equation, it basically meant that no matter how much I finagled the other variables, namely dr and v, m and q are constants, and it doesn't help that m is so insanely small, the machine would have to spin so fast that it would have inevitably torn itself apart, even if I had the mechanical energy to let it do so. I only had so much room in the cavern to make d bigger, and the bigger I made r, the larger the machine had to be, and the more mechanical energy it would have needed to spin it up. And if I made v too small, it wouldn't drive a strong enough current to electroplate at anything less than glacial rates. Whatever way I sliced it, the numbers just wouldn't let it happen. I guess that says something about the raw strength of electromagnetic forces compared to normal mechanical or gravitational ones. So I backed off for a minute, and tried to think about the other properties different elements had that I could use to separate them. I could literally filter them by size, but that would have taken some kind of nanotech filtering membranes. Not possible here, even if I could figure out how to turn charcoal into graphene and perforate it. Each element has a unique spectrum, but I couldn't think of a way to make that useful for separating them, other than maybe make one element hotter than the others, though it would spread that heat to them evenly, and even then, I don't think I could make a variable spectrum light source right now. The closest thing I could get to practical was that each element has a different melting and boiling point, so if I could get them hot enough, I could literally distill metals out of a mixture, albeit after several rounds of distillation, but that would take way more thermal energy than I'm ever going to have access to here. At that point, I was getting pretty frustrated. It would just be so much easier to separate them while they were in a solution, because they'd be easier to move around in that form, and I was sure there had to be a way to do it. I thought it would have almost been easier if I could evaporate the ions and put them in a big mass spectrometer like they used for enriching uranium during the Manhattan Project. Then I thought to myself that maybe I could, minus the evaporation part. A mass spectrometer basically works by shooting ions through a magnetic field, which deflects them in a direction perpendicular to both the field and the ion's path of travel. How much it can deflect them depends on their mass. Light ones are easier to push than heavy ones, and so deflect more. The equation for this deflection is F equals QVB times sine theta, where Q is the charge of the ion, V is its velocity, B is the strength of the magnetic field, and theta is the angle between V and B, and if we make sure they're always perpendicular to each other, this turns into a 1 and can be ignored. This means that charged particles moving through a magnetic field will always be bent into a circular path around the magnetic field, so centrifugal force comes into play again. If I want to know how strong the magnetic field needs to be for a given radius and speed, the equation becomes B equals mv over qr. So if I'm trying to bend, say, a lead ion with a mass of 4 times 10 to the negative 25th kilograms at a radius of 10 meters and at a velocity of, say, 1 meter per second, which doesn't seem unreasonable for flowing water, then the magnetic field I would need would be 0.17 microteslas, which actually doesn't tell me too much, other than that it's far less than the strength of even the Earth's magnetic field, which is about 250 microteslas. The equation for the magnetic field strength inside of a wire coil is B equals mu I n over L. And yes, this is another equation I never leave the house without, where mu is the magnetic permeability of the material in the center of the coil, I is the current running through it, N is the number of turns on the coil, and L is how long the coil is. Since the magnetic field would pass through water, it would have a magnetic permeability pretty close to that of vacuum, which is 4 pi times 10 to the negative 7th. So if I made a coil with about 1,000 turns and a length of 10 centimeters, then the current would be I equals BL divided by mu n, or 13 microamps, which is hardly anything, and the voltage to drive that current would be comparatively small, 20 microvolts for a 30 gauge wire, or 0.3 microwatts in total. In order to make this thing practical, I would actually have to make it smaller, though the upside of making it bigger would be that the ions would separate into rings with a larger difference in radii between them, so I wouldn't have to be as precise in the machine's construction. For example, if I separated lead into a radius of 10 meters, then thallium, one atomic number down, would separate to a radius of about 9.9 meters, or a 10 centimeter difference. If I put lead at a 1 meter radius, the difference would be about 1 centimeter, which is probably about as small as I could reasonably go. Of course, I knew it wouldn't work that easily, because the water, which is not affected by the magnetic field, would get in the way of the ion's motion. There's a reason they normally fill mass spectrometers with a vacuum rather than water. Still, you can't escape the fact that those ions would be experiencing that force. All the water could do is slow them down, like speed bumps on a hill, so by recirculating the solution, I would be able to winnow down each stream to be mostly the metals I wanted. The next complicating factor, though, would be the sulfide ions, which would try to stick to the metal ions and keep them neutral. This could be partially mitigated, however, if the cathode of the whole cell was in the opposite direction of the water flow, where it would extract most of the sulfide ions, leaving the net solution positive, flowing like an electrical current. I don't know exactly how fast the metal ions would move through the solution as an electrical current. Maybe quick, short bumps at near light speeds as ions collide with other particles and pass on their charge and kinetic energy through the water like a Newton's cradle. In In contrast, I could control the water's speed more precisely, which would, in its own way, replicate an electrical current, whether or not there's an actual electrical current. Just a bunch of charges moving together at speed. Either way, moving charges plus magnetic field equals separation, and I can't really think of any other major complications to the basic physics of it beyond the water slowing things down a little bit. At that point, I was singing and dancing for joy when I went to make lunch, not only because this meant I could have access to a virtually unlimited supply of metals, even rare metals with unusual physical and chemical properties, but because this is a problem that's been vexing the back of my brain for a long time. Once I'd calmed down a bit, though, I got to work designing a prototype to turn theory into something practical. One of the challenges was allowing the solution to both circulate and concentrate specific elements next to specific cathode plates, all while preventing the dissolved metal ions from mixing again, because there would always be a chance that a random, unwanted element could pass near enough to the cathode to get picked up, due to the law of diffusion again. This suggested the necessity for serial separation, which would require several stages of electrodes for each of the elements I could collect, depleting one element at a time from the solution before passing it on to the next set of cathodes. To aid this process, I could place the cathodes on the outside edge of the ion's curved path, so they would pick up only the ions circulating closest to them, and if the water near them was allowed to circulate for a while, the cathodes would continue pulling those metals out of the solution for as long as the water circulated. This was not unlike my previous idea for many belts separating each element from the solution one at a time in stages, and likewise it suggested the option of modularity. I could make a single cylindrical pot to act as both the cathode and mount for a magnetic coil for each individual element, allowing the depleted solution to pass on to another identical cylinder, but with a slightly weaker magnetic field, perhaps by adding a small resistance between coils. I could build these cylinders in a stack and let the solution flow through it, becoming more depleted of heavy elements with each stage. Either way, I'd need some mechanism to keep the water both stirring evenly in each cylinder and draw it out from the center, where the lightest elements would be forced to concentrate by the magnetic field. It struck me that another rotating cylinder inside the cathode pots would produce the most even rotational flow, as water would drag along its surface, and I would be able to control the rotor's mechanical speed, and thus the speed of the circulating water, quite precisely. The next issue I considered was how to pump water and mechanical energy through the stack. I considered pumping water up through the center of the stack using an Archimedes screw to also provide mechanical power to the rotors. However, I soon realized that this would be a bit too complex and prone to leak or waste mechanical energy. I decided it would just be easier to pump the water straight to the top of the stack and let it dribble down, overflowing from the center of one cell to the edge of the next. I figured I could also make each cell slightly conical, which would allow me to tip the cathode plates and slide them in and out easily, while still keeping the stacks contiguous. It would throw off the centrifugal force of the magnetic field equations a little, but it shouldn't be a problem if the angle is shallow enough, and the major radius is still larger than the deflection radius of the ions that cell is meant to collect. Next, there were a few questions to answer about how big this thing needed to be. There are about 50 metallic elements that I can collect via electrolysis. Not that they would all be collected in even quantities, but if I did want to get them all, that would require a stack of 50 cells, and if each cell were 10 centimeters tall, the whole stack would be 5 meters tall, or about 2 stories, which would basically turn this into one last major construction project for the end of the year, though nothing too crazy, I suppose, at least in comparison to what I've already done. There are also about 10 alkali and alkali earth metals that I can't collect as metals, but might still be able to separate as hydroxides that would need to be removed from the rest of the solution before being passed on to the next stages. The only way I could think of to do that was to let the hydroxide solutions near the cells dribble out into a nearby container, where they would be separated from the rest of the solution, keeping the overall concentration of alkalis low. I realized, though, that this could be controlled more precisely if I made a wall or lip in the cell between the rotor and the cathode, where the metal ions would be expected to collect. The ion-laden solution would tend to splash over this wall and collect at the electrode, keeping it separated from the rest of the solution. This, in fact, would be a helpful addition to all of the other cells. Finally, there would be a lot of hydrogen sulfide being produced at the anode of this whole apparatus, which I would like to keep out of the cavern's air supply, as it is poisonous, and would also like to collect and recycle back down into the earth as sulfuric acid to continue dissolving metals out of the magma. There are also 5 halogen gases that could be produced at the anode, which are highly toxic and potentially useful for various applications. Another fractionating column would therefore seem to be in order, except for the fact that pure halogen gases like chlorine and fluorine don't really condense at normal temperatures, though they can be dissolved in water temporarily. Instead, it might be beneficial to have one additional electrolysis cell added to this whole apparatus, which could produce hydrogen and oxygen gases from the water. The hydrogen gas could be bubbled into the main anode, where it would react with any free halogens and sulfur ions, producing hydrochloric, hydrofluoric, and sulfuric acids, which could then be condensed in the fractionating column, leaving mostly pure oxygen to escape into the cavern. One last thing that could be added to the anode would be a similar magnetic field to help force separation between dissolved ions, forcing the negative sulfide ions into the anode for neutralization and conversion into sulfuric acid, while driving the positive metal ions away for separation at the various cathodes. At the bottom of the stack, metal-depleted water could have the hydrogen and any residual metals extracted from it before being mixed back in with the sulfuric acid water and poured back down into the geothermal well for continued extraction. Hot metal sulfide-rich water would then shoot back up to the top of the stack, turning the turbine, which would turn the rotors and generator, and get pumped through the system again, using the return pipe as the axle for the turbine and rotors. I'd need to make some modifications to the turbine, however, to make it more resistant to sulfuric acid, though hopefully by that point a lot of the acid would be neutralized by bonding with metals. In case the whole apparatus stopped for some reason, or sprang a leak, I would need a reservoir at the bottom of the stack to collect any acid water that might spill out. The anode would need to be at the top of the stack so the negative ions could be separated from the solution immediately before the positive metal ions were winnowed out, which would make the overall stack a bit taller and perhaps a bit top-heavy, so the entire apparatus will need a superstructure to support it. A small tower with a spiral staircase between levels should be adequate. That was a lot to figure out, so to summarize, I'll need 60 shallow conical cathode pots, 60 matching clay rotors, an acid-hardened pipe/axle to mount them on, 61 copper wire coils, a potentiometer and resistors to help tune the coils to the correct currents, one additional fractionating column and anode chamber, one additional hydrogen electrolysis cell and piping to get the hydrogen back to the anode from the bottom of the stack, an acid-hardened upgrade to the turbine, and some modifications that'll allow it to remain connected to the axle pipe and vent steam and acid into the sealed anode column, while simultaneously allowing it to continue generating power. That last part will be a bit tricky, because the turbine is basically going to have to be inside the anode column while it's running, or at least in line with it while still maintaining a mostly airtight seal. Unless I redesign the turbine casing to be part of the fractionating column. I can mount the generator belts to the shafts sticking out the top, kind of the way it is already. I would have probably needed to rebuild the turbine from the ground up anyway. Oh yes, and I'll also need a concrete superstructure for the whole apparatus, but I'm getting ahead of myself. If I'm going to make a prototype, though, I should probably only make a handful of the electrofuge pots right now, and focus on using them to extract any copper from the existing hydrothermal solution, which will save me from having to mine it. I can let the heavier elements drip from the outside edge of the pot, and collect the copper more or less from the middle. I should also be able to mount it to the turbine as is, with minimal modification. With a plan in place, I had just enough time at the end of the day to build a handful of the prototype electrofuge pots and rotors, and leave them somewhere relatively warm to dry overnight. Week 49, Day 2. Perfect. It was a clear day today, so I immediately set my electrofuge prototype pots in the kiln in the morning, before conducting my morning forage and microbe selection routine. The yeast cultures in particular seem to be almost done, as I started them a bit earlier than the others, so at this point I'm mostly separating them into cultures with better or unique flavors, as I'm not taking them in large enough doses yet to determine if they have any adverse health effects. However, my mind was mostly focused on the electrofuge project, and around lunchtime, I took my pot parts out of the kiln and down to the shaft, where I began disassembling the turbine and installing the electrofuge pot. For now, I only installed one electrolysis plate at the radius I expected copper to collect at, and built a frame to support the pot on top of the reservoir and the turbine on top of the pot, with the water from the turbine discharging into it as gently as could be managed. It wasn't going to separate anything without some copper wire, though, so since I planned on doing most of my electroplating down in the shaft from now on, if this project works, I decided to temporarily dig up the connecting cables between the workshop and the lab. It should be enough for the simple coil I need to build, and easy enough to replace later. I also grabbed a couple of spare resistors from the lab, along with my ammeter, and tuned the coil, plate position, and rotor speed so that the plate would collect mostly copper once I hooked it up to the generator for electrolysis. It took a while to finish tweaking it so the turbine wouldn't topple over or leak too much, but once I had it set up, I basically left it in the hands of physics for the night. I intended to spend the last couple of hours in the evening getting back to my Half-Life writing, but I couldn't get the electrofuge off my mind. So instead, I spent my time doing some more in-depth design work for the electrofuge and supporting tower, and double-checked my numbers before going to bed. Week 49, Day 3. It was partly cloudy this morning, but that didn't concern me nearly as much as checking on my electrofuge first thing in the morning. It did work, but with a complication. Because that one plate had most of the power from the generator being pumped through it, it did indeed collect most of the metal in the band dictated by the magnetic field. However, it wasn't the metal I was expecting. Instead of dull orange copper, I found a few slivers of a dull gray metal with pretty aquamarine specks around the edges. I was concerned that I'd gotten an amalgam of copper and other adjacent metals because of this, and immediately started testing it to find out what exactly it was. I was able to narrow it down almost right away by the fact that it kind of wanted to stick to the core of the generator. There are only two metals I know of that are magnetic, iron and nickel, and both because iron was supposed to be several bands away from the expected copper, and because this metal turned out to be a little denser than pure iron when tested in the lab, I concluded that this was probably nickel, which I'm actually pretty excited about, as I understand it to be a somewhat rare element. It was probably amalgamized a little bit with other adjacent metals, like copper and cobalt, which told me the coil needed a little more tuning, and that I needed to aim on the high side of my atomic mass estimates. I adjusted the coil resistance again, and got the idea to paint both sides of the electrolysis plate with carbon. This would allow it to collect elements in both the target band as well as any bands above it to keep them from interfering with the results of future tests. Once I made these corrections, I restarted the electrofuge and proceeded with my morning chores while it was nice out, and did my microbe separation before lunch. After lunch, I considered the results this morning to have been enough of a success to warrant going into full production. So I spent the remainder of the afternoon and early evening building 10 of the pots and rotors necessary for the full stack. Week 49, Day 4. A heavy storm blew in last night, which I wasn't really expecting, and it woke me up a little early. I had to take my headlamp and batten down all the hatches in a hurry before it got too much worse. I thought the bad storms were over for the season. This didn't hamper my projects today, though. I separated my microbial cultures again first thing, though I was a bit tired, and then headed down to the shaft to check on the electrofuge. To my delight, I could see bits of copper starting to grow on the plate already, which is an exciting sign that I've got the speed, magnetic, and electric fields dialed in. I then began building a frame for the tower, which I'll fill in with claycrete later. Good thing I moved most of my lime down into the caves for storage anyway. I was able to reuse a lot of the bamboo from the broken pipe hopper, and I had plenty of bamboo and construction wood stockpiled in the tunnels. Compared to some of the other structures I've built, this one was pretty much child's play, especially since it didn't have to be very big. I decided to make the individual cell pods half a meter in radius, about the same size as the original reservoir, so that everything would stack neatly. From there, the tower walls didn't really need to be that much wider, about another meter on each side, as its primary purpose is just to stabilize the electrofuge stack, distribute the weight of it so it doesn't collapse on itself, and create a means for me to access each layer of the stack. A spiral staircase will do nicely. Technically, the tower didn't even need a set of outer walls, as there was no weather in the cave to protect the interior from, but I was going to need something relatively strong to hang the staircase from, so I figured I might as well. I started with some bamboo support rods for the central stack, with some horizontal cross braces between them, which the pots will be able to rest on later, providing support in tension as well as compression. Then I started building the framework off of it for the spiral staircase, up to the height where I couldn't reach the top of the stack anymore. Then I finished building the framework for the wall around the rest of the first level, and I decided I might as well give it distinct levels for extra support and storage space if needed. I left an arch for the doorway, and then headed back upstairs for lunch. The weather had barely let up enough for me to get to the other buildings in the compound, and I decided to spend the remainder of the afternoon and evening in the workshop, making another series of pots for the electrofuge, so that when the weather lets up, I could make full use of the kiln. Week 49, Day 5. The sun came out today, like the storm yesterday never happened, though the debris littered all over the courtyard begged to differ. I immediately slipped my pots into the solar kiln in the morning, and then did a quick rundown of all the structures that needed repairs after the storm. I tied the wind turbine sails back on, and fixed any maladjusted plates on the solar array before doing my morning chores and checking on my microbe cultures. At about lunchtime, I removed one batch of electrofuge pots from the kiln and put the other in for the rest of the day. I checked the barometer after lunch, and unfortunately, the pressure was dropping fast already, suggesting another bad storm was probably on its way. I left all the hatches battened, and spent the afternoon building pots again, before locking down and moving the finished pots back down into the tunnels for tomorrow. Week 49, Day 6. As predicted, it was another rainy, blustery day, so I processed my microbes in the morning. They seem to have finally gotten the message of what traits I wanted them to express, and are starting to specialize for them at an increasing rate. After that, I headed back down into the tunnels and took the finished electrofuge pots with me. However, I didn't install them right away, because the copper collecting prototype was still at work, having already collected an appreciable amount of metal already, which I peeled off and set aside for later. Instead, I decided to start filling in the framework I already had for the tower, so I'll have something strong to continue building on next week. The tower is mostly cylindrical, so if the section I'm working on is about 1.5 meters in radius on the inside, 2.5 meters high, and if I give it walls a thickness of about 5 centimeters for strength, it should have a volume of 1.19 cubic meters, or 43 cubic feet. I should need 79 liters of lime for that, and it should take me about 45 minutes to slap the claycrete into place, though I'll probably have to spend at least an hour moving the water, lime, and clay up and down from the tunnels where I have them stored. Wheelbarrow should help with that a little. If I want to add a hemispherical roof on that, I'm going to need another 48 liters of lime, and 26 minutes to fill it in. Probably a little more to make it flat for the second level. Finally, if I want to fill in the staircase, which I could approximate as a disc spread across the cross-section of the tower, that's going to be another 23 liters of lime, and 12 minutes or so to fill it in, giving me a grand total of 150 liters of lime and 81 minutes to fill, though I'll probably need twice that much time for running up and down the tunnels. I can probably repeat this calculation for the second level, and fortunately for me, I've already got 300 liters of lime stockpiled, so I should have enough to finish building this thing without any significant interruptions. With that calculated, I spent an hour or so delivering my materials to the worksite before getting started. I was tempted to try using one of my electrofuge pots as a cement mixer, but I didn't want to risk gumming up the mechanisms, or the sulfuric acid messing up the concrete chemistry. I just mixed it by hand, one small pot at a time, before setting it in place in the wall framework. I could tell from the vaulted roof framework I made yesterday that the roof wasn't going to need quite as much concrete as I called for, as it would be intersected by the staircase. The overestimate should still be good enough, however. I got to lunch a bit late, and spent the late afternoon making another batch of electrofuge pots. I got pretty sick of my hands being all mucked up with clay and concrete today, but at the same time, it makes me look forward to having the day off tomorrow. Week 49, Day 7. The storm was still raging this morning, which I was a little surprised by. I expected the weather to mock me again for the Sabbath. I bore with it, however, and checked on my microbial cultures before listening to the sermon on the radio. Transcribing my recordings after that took twice as long as usual, because I was so busy last week that I didn't realize I'd forgotten to do it. I then went to the underwater dome for lunch and fed the sharks again, which seemed pleased that I was back. Once I was done down there, I came back and spent the rest of the afternoon getting back to my Half-Life writing, specifically the Power Up chapter, where I had to introduce the Gargantua. It wasn't a difficult encounter to balance, though, because it's immune to all of the player's weapons. I did my best to introduce as much tension as I could, because all you can do is run. Having made the soldiers encountered so far very difficult to fight, adding the gargantua, which just wipes the floor with them in seconds, was meant to add the feeling that not only are things getting worse, but that there's nothing you can do about it. Until the end of the chapter, when you finally do kill the gargantua, not with guns, but with brains, to signal to the player that maybe by being smart, I can beat the unbeatable. That's a good message, and one that seems appropriate for everything I've gone through so far on this island. And with that, my tongue had decided to go home early, so enjoy the blooper reel. I had nothing else left to say. It probably has to do with the fact that in any case, I think I've got 1 month to go before I think I can count. I don't need to be able to count, I need to be able to read around the various seams where heavier metals would stick to the heavy, and V is the voltage between the electrons. No, was that each element has a different melting or boiling point. If I want to know how strong the magnetic field needs to be, 20 milliohms. What the heck is a milliohm? I'm making up my own units of measurement here. Would extract most of the metal sulfides ions. Okay, bug. There's a bug here. Pause for edits. Just a bunch of charges moving. At that point, I was singing and dancing for joy when I went to make lunch, not only because this meant I could have access to a virtually unlimited supply of metals, even rare metals with unusual physical and chemical properties, but because this is a problem that's been vexing the back of my brain for a long time. No joke, when I actually figured this out sitting in the back of that cursed mail van while it was raining outside, I literally started going, I'm singing in the rain, just singing in the rain. What a glorious feeling, I'm happy again. My electrolytic centrifuge, the physics did firmly refuse. But I appeal to magnetic field. Now mass spectrometry makes dissolved metal ion separation easy. And if the water near them was allowed to circulate for a while. Are you done? While still keeping the which I would like to keep out of the cavern's airs. Which I would like to keep out of the and leave them somewhere relatively warm to dry overnight, and leave them relatively warm to dry. And with that, my tongue is completely worn out. Blah, 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 blah. And that was just day one. I was able to narrow it down almost. I was able to arrow it down. I've been talking for too long. I was Pause for edits. Resume. Scratch. Which I'll fill in with clay cleat raider. I've jinxed myself. Now that I've gotten the line right, I've lost my spot. Then I started building the framework off of it for the spiral staircase, up to the height where I can't reach the top of the step. Okay, typo. I immediately slipped my pots into the solar kiln. There, okay. My eyes are skipping lines. Bleh. I am not making this easy on the editor, am I? As it would be intersected by the Almost done. You can make it. I bore with it, however, and checked on my microbial cultures before listening to the sermon on the radio. Hold on. transcribing my recordings after that to transcribing my recordings. I came back and spent the rest of the nooning. My ability to speak and read have completely gone. Hey there. Thanks for listening all the way to the end of this particularly long and technical episode. I'm just really proud of my electrofuge design. And although I'm certain that there would be a lot more complications to it in real life, as far as I know, the basic principles are sound, so it should work. If you want to find out how I progress with it on my imaginary island, though, you can press the subscribe and bell buttons to get notified as soon as the next episode is ready. Now, although I haven't patented this yet, I'd like to test it first, please don't steal it in the meantime, and patents are ridiculously expensive, I'm not going to monetize these videos to try and pay for one. It would take forever anyway. However, it helps me out in a much more real and personal way that you've watched the video this far. And it would help me out even more if you could share this video with someone else who you think would be interested in this sort of thing. And since you liked it enough to watch it to the end, you can press the like button to say so, which would also help me out by telling the algorithm to do a little bit of that sharing for you. Also, if you'd like to chat about some of your own stories or perspectives on the episode, even reasons why you think the electrofuge might not work after all, feel free to share them in the comments section below. I genuinely love to hear them, and I really am open to suggestions and corrections, as long as they are informed and well-intentioned. I don't think anyone goes out of their way to invite wanton criticism. That said, thanks again for listening, and hope to see you here again next week.